So we're going to start this unit discussing cryptography. I'm going to give you a quick introduction to a little bit about the history of cryptography, and then we'll talk specifically about how cryptography works in most modern implementations of cryptography. And then following this presentation, there's another presentation that discusses some of the standards and protocols that are widely in use. And we're going to talk more broadly about standards and protocols. We'll talk about that later on. So first, a quick introduction. So cryptology is the science of encryption, which is cryptography and cryptanalysis. So, the algorithms and the math behind cryptography, how it works. And really the mathematics behind cryptography is pretty fascinating. So if you find it interesting, I highly recommend taking a look at it. And you can certainly read more about it. Cryptography involves making and using codes to secure messages. And cryptanalysis is cracking or breaking encrypted messages back into their unencrypted origins, so how to break cryptography. So cryptology has an extensive history in lots of different cultures. Just about anybody who wants to hide a message used cryptography of some kind or cryptology. There is evidence of cryptology going all the way back to ancient times, to the Romans and the Greek and so forth and so on, all the way up to today, where almost all popular web browsers have built-in encryption features for securing e-commerce applications, for example. And that's just a little blurb from your textbook. There is a restriction on export of crypto systems, which is important to understand. So after World War II, the United States government and many other governments considered cryptography to be a munition because of its importance in defense and in war. So there is a restriction on export of cryptography technologies, which is really getting complicated because we use cryptography so much in online transactions on the internet, and the internet doesn't really have boundaries like we do in the real world. It's very easy to have transactions going across international borders. It happens all the time. And almost everyone employs these cryptography standards that we talk about in this course and in the follow-on courses. So I'm not sure. There are some cryptography standards that are probably more closely guarded for sure. And of course, the methods and techniques for cracking cryptography, of course, is closely guarded secrets. I have to believe that a lot of cryptography that we use for things like e-commerce, it's probably easy enough for governments to crack it that they're not as concerned that that's being exported and being used by foreign countries because, they probably have the ability to crack it anyway. So some of the vernacular for cryptography, we have algorithms that we'll talk about, different types of ciphers I'm going to talk about, and crypto systems. We'll talk about code, decipher, decrypt, which is to unencrypt something, and cipher, which is to encrypt something. The key, we'll talk about the key. We'll talk about the key space. Plain text and clear text is a message that hasn't yet been encrypted. And then we'll talk a little about steganography and how difficult it is to crack certain types of encryption. So I'll talk a little bit about some of these terms, but these are all defined in your textbook. So I certainly encourage you to take a look and get familiar with some of this vernacular, which you would want to know. So some cryptographic concepts. So a cipher. So originally we had simple algorithms used to hide messages. It's very simple algorithms. You can read about them on Wikipedia. And of course there's some blurbs in your textbook about this, but there were some older, very simple algorithms prior to World War II, when encryption was rather simple. Things like substitution algorithms, substitute certain letters for other letters, one-time pads and things like that, till today, after World War II. So World War II is where cryptography and the science of cryptography really started to get more complex. I'm sure most of you have heard of the Enigma, which was the machine used for encoding with the Germans, which was cracked eventually by the Allies. But that was all very difficult. It was a very complicated system. And of course, the United States and the Allies had their own systems for cryptography. That was one of the big things that came out of World War II and has followed us ever since is considerable advancements in the field of cryptography. So modern cryptography, which we call encryption, we start with plain text. Ciphertext is what has been encrypted. The key is what we use to encrypt it. Cryptanalysis is the study of modern encryption. So first, there are two major types of encryption. Well, three really. We're going to talk about, in this course, we talk about symmetric encryption, asymmetric encryption, and we'll also talk about hashing, which is a one-way encryption where you can only encrypt, but you cannot unencrypt the data. You can't decrypt the data. So symmetric encryption is pretty simple to understand. Basically, you start with a message and you have a key. So you have an algorithm where when you use that key with the algorithm, you end up with ciphertext using that key. You send your message to another party. They have the same key with the same value. They unencrypt the message and they can read the message in plain text. If someone were to intercept that message in transit, they would have to have a copy of that key. Now, one of the problems with this system of encryption is that both parties have to have that key. But the advantage to this system of encryption is that it's extremely fast and very secure if you can keep the key secure. So you can have very complex keys with very secure encryption, and it can be very fast. The problem is you have to keep that key secret, and somehow each party has to somehow acquire the key. They have to somehow get a copy of the key. And how do you do that securely in a in a transaction that has to happen one time or very quickly? So that's certainly a concern. So enter asymmetric encryption, which sort of fixes some of those problems. So with asymmetric encryption, we start with our message. So if I had a key, if I wanted someone to send me a message, first I would send them a key that is used to lock the message. So I have two keys. One key is called a private key. The other key is called a public key. The public key I can give out to anyone. The only thing you can do with my public key is encrypt the message using that public key. You cannot decrypt the message with the public key. It's mathematically impossible. Well, not impossible, but very difficult. So we start with the public key. So I give my public key to the sender. The sender then encrypts the message with my public key. They send it to me, and I can use my private key to unencrypt that message. So you can see the advantage here is I don't care if somebody gets my public key. The only thing you can do is lock a message, is create a message for me. You won't be able to unencrypt it. So I can give that key out to anyone. Anyone can download it from my website or whatever. It doesn't matter. Anyone can have that public key, and it's not going to harm me. I just have to make sure that I keep my private key private. So this does solve one problem. It solves the problem with having to keep the same key. In this case, if I were trying to communicate with somebody using asymmetric encryption, I don't have to worry about keeping the key secure and exchanging it. I can just simply give them my public key. They give me their public key, and we can encrypt messages for one another. So, for example, we could, via email, we can exchange our keys, and then I can start encrypting using their public key. They're encrypting using my public key, and we're exchanging messages, and everything's fine. It's very secure. One downside of asymmetric encryption is that it is, it's more complicated than symmetric encryption. Symmetric encryption algorithms are much easier to implement, and they can be done much faster. They require less processing time and so forth. An asymmetric algorithm is much more complicated. It requires more processing time on the computer, so it does tend to slow things down a little bit. So you have a little bit of overhead when you're using asymmetric encryption. So that's certainly the downside. So our problem is we have one algorithm, which is very fast, but less secure because we have to somehow share a key, and another algorithm that's extremely secure, but much slower because of that key exchange. So we're going to talk a little about session keys. So like I said, asymmetric is superior security through the public key. Symmetric encryption is more efficient, but it requires a shared key. And we can't rely on a shared key. We can't rely on sharing secrets because there's an old saying, three may keep a secret if two of them are dead. The bottom line is you can't share, by the way, Ben Franklin said that. We can't share a key and not expect it to get compromised somehow. So we can't rely on shared keys. It simply isn't going to work. So shared keys should be limited to just a single session, and we should be able to exchange keys. So let's see how this works. So now we're going to do a hybrid of both of the encryption methods I talked about, of symmetric and asymmetric. We can use both at the same time. So we could start with exchanging our public keys. So I give my public key to them, they give my public key to me. Now I can use that public key to set up a communication channel just to negotiate and exchange a symmetric key. So we use the public key to create a secure connection that we can then use to share our symmetric keys, or to somehow come up with, agree on a symmetric key. And most of the algorithms that employ this method have some method of generating that symmetric key. So once they exchange public keys, then they can work with each other to generate that symmetric key. Now that you have a symmetric key, now you can use the symmetric key to exchange information much more quickly. And that symmetric key has a lifetime. So every so often, when its lifetime expires, you renegotiate a new key, which helps with security. So we don't have a shared key for a long time. So if it does get compromised, it reduces our exposure. So again, we exchange public keys, we use that to negotiate a symmetric key, and then we can leverage the better encryption algorithms, the faster encryption algorithms with symmetric algorithms to exchange information. So the payload, the actual data that we're exchanging, that's being encrypted with symmetric key encryption, because that's the bulk of the encryption and it needs to be very fast. But to get that symmetric key, we use the slower asymmetric key exchange. But that's okay, because we're only negotiating and establishing a key that has a lifetime, that has a finite lifetime. So that's basically how key exchange works. One thing I didn't mention here, and I don't think your book really talks about it too much, but we go into this in much more detail in IT Security 2 and in your cryptography courses, you would discuss this, but that public key also can be used for trust. So when we exchange our public keys, we can also use them for certificates, which can establish the identity of the person that sent you the key. So we can make sure that we are encrypting the data for the right party. You certainly wouldn't want to get a public key that's really for an attacker, right? So let's say an attacker took the public key that was sent, that you're trying to send to someone, they intercept the public key and instead send their public key, so that they would be able to read the data that you're trying to send, and then they would simply use the real public key to encrypt it. It's kind of a man-in-the-middle attack, or a variation of a man-in-the-middle attack, and certificates is what allows you to detect that type of attack. And again, that all happens with PKI, public key infrastructure. But again, we don't talk about that too much in this class. That's discussed in much more detail in IT Security 2 in your cryptography classes. So, fundamental methods. So the components of encryption, you have an algorithm, a key, and a key exchange. Anytime you're setting up an encrypted connection, some of the things that you'll need to know with your peer is what algorithms you're using for both the symmetric and the asymmetric components, and how you're going to exchange keys, or how you're going to establish a key. And there are different algorithms to do that. And in IT Security 2, we talk about specific ways to do that and specific algorithms and how that works. Most encryption standards can be broken down into either block or stream. A block-based cipher is large contiguous blocks of data that are encrypted, where a stream is bit by bit, or byte by byte, or a character stream. Most encryption algorithms are block algorithms. There are a few that are stream algorithms. If you in the lab, I'm going to ask you to use OpenSSL to experiment with a little bit with encryption. And if you run the command, you'll see a whole bunch of encryption algorithms. And I think in OpenSSL, the only one that's a stream algorithm is going to be RC4, I think, which is actually not a very good algorithm to use. It does have some issues, some vulnerabilities that have been exposed recently. But almost all of the other ones you'll see in there are block. So block is definitely much more common. So traditional asymmetric encryption, the way it works, mathematically the way asymmetric encryption works, where we do that key exchange, is it's based on the idea that multiplication is very easy and fast. Most of us can multiply very quickly. However, factoring is much slower and a lot harder. So if I gave you two numbers and told you to multiply them, that's relatively simple. So if I gave you, 936 times 465, most of you could figure that out relatively quickly, multiply those numbers. But if I gave you the product of those two numbers and told me to find the factors that can create that product, that would be much harder for you to figure out on paper, for you to figure out what those factors are. That's what factoring is. It's taking the product and you're trying to figure out how you arrived, what factors would allow you to arrive at that product. Sit down and try it. It's slow. It takes a long time. And that's known as a trapdoor. It's easy to go one way, but very difficult to go the other way. So it's very easy to multiply, but very difficult to find the factors. So it's hard, but not impossible. Computers are very good at those tedious tasks, given a small enough number. So that example that I just gave you, if I gave you that product and we told the computer to try to find the factors, they would probably discover the factors relatively quickly, probably in the seconds. However, if you have a large enough product, it gets much more difficult for a computer to figure those out. And one of the ways that most traditional asymmetric encryption works is it's based on using factors that involve prime numbers. So you only have a very limited number of possible factors. But again, it's hard to factor those, but it's not impossible to factor those. It could be done. Computers can do that. So elliptical curves is a little bit different. So while it's very difficult to factor, and very slow and hard to do factoring, elliptical curves are much more complicated. It's much more complicated math. So elliptical curves usually involves analytical geometry, right? So it's trying to calculate curves, basically, if you remember from your calculus classes. So given points on a curve, it is mathematically impossible to discover intermediate points in that curve. So if I give you points on a curve, it's mathematically impossible to discover intermediate points. So this is a much better trapdoor. It's a much stronger trapdoor than we have with factoring. So it gives you much better encryption. You can read about this. There's a little write-up. I have a URL here in the presentation, which of course you can download the presentation to click on it instead of trying to write it down. But that's a nice little primer on how elliptical curve cryptography works. One thing that's interesting about elliptical curve cryptography is that it's much easier, much faster to work with elliptical curve to have the same level of security as traditional asymmetric encryption. So with much less processing time, you can do much better security. You have much better encryption or much better key exchange algorithms. So this would be common in any area where processing time is at a premium. And one of the reasons I think this is coming up more often is because devices are getting much smaller, and it's becoming more and more important for them to be more efficient. So this is one way you can have more efficient encryption that is just as effective as asymmetric encryption, or more effective than asymmetric encryption. So this is, of course, a recent development. Encryption, elliptical curve, has been around for a while, but it's really just starting to gain traction at the time of recording this. It's really started gaining traction in the last couple of years. Quantum cryptography is a little more complicated. So quantum computing is really in its infancy, but it relies on the principles of quantum mechanics, like superposition, entanglement, all these complicated things. If you think back to your physics class, if they talked about quantum mechanics, it's a it's a very abstract concept, quantum mechanics. But here's the idea: if you have a computer that is extremely powerful, then it's possible that all of these standards that we're talking about, where it takes computers a very long time, for example, to factor, right? So one of the ways that you could crack encryption is by factoring. And if it takes computers a very long time to do that, if they're standard computers, if they're quantum computers, maybe they'll be able to do that much more quickly. So one thing that people worry about with quantum computing as far as cryptography goes is once quantum computing comes into common use, it may be possible for someone who has a quantum computer to crack cryptography much more quickly than they would be able to on a traditional computer. And we're already starting to see the implementation of quantum computers. So we're getting there. It's going to happen at some point. Another area of cryptography affected by quantum mechanics is keys. So one of the things one of the things that takes more time in most traditional cryptography is that key exchange, because we're using an asymmetric algorithm that's not as it's not as fast as symmetric as I talked about before. So one of the odd things about quantum mechanics, one of the things that they talk about is measuring data disturbs the data. So if somebody intercepts the key, just by intercepting it, it would be possible to know if a key has been compromised. They don't have to do anything with it. They don't have to change it. If they just observed the key, the theory goes that you would know that it's been compromised. And I know this sounds very abstract, and it sounds like this is something that's very futuristic and probably isn't around. There are already commercial systems that use this concept, that have implemented this concept with quantum computing. So It's already starting to happen to some extent. And of course, like I discussed, quantum computing has amazing computational power. So that's really kind of one of the other areas that we're worried about is, if a large government's able to build a quantum computer, they might be able to crack encryption very easily. All right, another concept with cryptography. So I talked about asymmetric encryption and symmetric encryption. Symmetric being, the simpler one that's very fast. Asymmetric being a little more secure, but a little bit slower because it has the secure key exchange. But in both of those, we both encrypt and decrypt the data. We do both. Hashing, on the other hand, we only encrypt the data. So we don't actually unencrypt the data. And how is that useful? So take, for example, let's say I've got a document, right? So take a look at this document. I copy and pasted this from one of my credit card agreements. And if I took this credit card agreement and I use, say, the MD5 hashing algorithm. So there's an algorithm called MD5. It's a one-way hashing algorithm. It's a rather old algorithm. It's been around for a long time. It does have a few flaws, so I don't know that I recommend it, all the time. But I used an MD5 algorithm to hash that credit card agreement, and it gives you a fingerprint. So when you do an MD5 hash, or any hash really, it gives you a fingerprint, or that long number you see on the right-hand side that uniquely identifies that document. Now, if I make just a small change, so notice in the version at the bottom, I made a very small change. I said we will not assess a late fee, and that a returned access check fee will be 25 cents. So I changed it from $25 to 25 cents. If I showed you that document without highlighting my changes in red, if I showed you these two documents, it would be very difficult for you to tell that they're different. They look mostly the same, right? You really wouldn't notice that small change. However, if I do an MD5 on that file, notice the hash. It looks completely different than the first hash, even though I made an extremely small change in that file. It's a minuscule change. It completely changed that fingerprint. And that's really the goal with MD5 is that we can take just about any file, any document, any electronic, any digital file, use MD5 or any hashing algorithm. They all do this. There's different hashing. In fact, if you look in OpenSSL when you do your lab, you'll see a whole bunch of different algorithms for hashing or one-way algorithms. But in any case, it makes it incredibly obvious that something has been changed. So we can use it to compare files and we can use it for trust. And that's usually where we see hashing. Another area that you'll see hashing is in password storage. So, one way you could store passwords is to store them in an encrypted file so that if somebody goes to log in, you go in and unencrypt the file to find their password and you compare it and et cetera, et cetera. But hashing is actually much more secure in that case. So you take a user's password, you run it through one of these hashing algorithms and you get a fingerprint. You store the fingerprint and not their password. So their password is never stored anywhere. The only thing you store is the hash from their password. So when somebody tries to log in, they put in their password. We simply compare the hash output of their password to the stored hash, and if they match, the user is authenticated, and if they don't match, the user is not authenticated. And the user would have to somehow figure out how to construct a password that produces the same hash, which for most hashing algorithms should be extremely difficult, if not impossible. That's actually one of the problems with MD5 is people have figured out ways to make MD5 hashes match even though they're different values for the source file, which is something that should not happen, but it is possible with MD5 to do that. So that's why it's not considered a secure algorithm anymore. Although I should say that it is difficult to do that. It's not something that's easy to do. There's no free tool that you can download that makes it extremely simple that it take 2 seconds. You do need some significant computing power to generate different files that would produce the same hash. But it is possible. There are other algorithms, and certainly in IT Security 2, we discuss all these different algorithms that are used for things like hashing. I did talk briefly about digital signatures before, which in asymmetric encryption with the private key and the public key, that's used heavily in digital signatures, and we'll talk more about that in much more detail in IT Security 2. So if you're going to take the follow-on course, IT Security 2, we'll certainly cover digital signatures at that time. So some of the objectives with cryptography, perfect forward secrecy, transport encryption, right? So we want to have our data encrypted while it's in transit or even while it's stored. Non-repudiation means not being able to deny that you sent a message. So I shouldn't be able to send a message and then have somebody think it came from someone else. That's non-repudiation. Encryption allows us to do that through trust. One of the concepts is in encryption is key escrow, which is the idea that we store our keys in some kind of an escrow so that they can be used to decrypt later on if we do not desire to have it encrypted. And that's been one of the it's been in the news a lot lately. Actually, if you followed the in the news when I'm recording this, perhaps about 6 months to a year ago, there was a story about Apple where the government wanted access to the data on a suspect's iPhone, and Apple refused to do that. So that's an example of where key escrow, if we had key escrow in that case, the government simply would have been able to go to the third party with the key, and they would have been able to get access to that data. So that's the sort of concept. Steganography, which I don't talk about too much in this course, but in the follow-on to this course, we have some labs where you can do steganography. And basically, that's hiding a message in plain sight. So steganography is hiding in plain sight. A good example of that is you could take an image file and you could hide a message inside an image. So somebody might look at the image and recognize it as an image, but they wouldn't think to look inside the image for a hidden message or inside the digital file. And you would have to open the file with a hex editor, and maybe in the header buried somewhere there might be a hidden message. But who would go and look for that, right? So I could take an image with a hidden message, put it out on the internet, and anybody could go and look at that image and probably wouldn't know that there's a secret hidden message in there, but somebody who knew the message was there could go and look at that message. So it's not cryptography in the sense that you're scrambling you're using some algorithm to scramble the message so that it can't be read, and using keys and all that sort of thing. It's just hidden in plain sight. I would say that you can't rely on things like steganography, but it's good to understand what it is, and that attackers can tend to use steganography to hide messages. All right, so in the next presentation, I'm going to talk about some specific standards and algorithms that we use in IT security for trust and for secure communication. And again, I'm not going to talk about specific standards that we employ within those, but I'm going to talk sort of about the high-level standards. So that'll be in the next presentation.